We are Team Orbit presenting our satellite challenge mission ID 246. Our project is designed to collect, process, and transmit real-time flight data during the mission. At its core is a teensy 4.1 microcontroller that handles sensor data, onboard storage, and wireless communication simultaneously. The payload includes sensors for altitude, temperature, humidity, acceleration, air quality, and GPS tracking, along with a 5 megapixel camera to capture the flight visually. To improve stability during descent, we use three-axis stabilization system with brushless DC motors and flywheels to reduce oscillation. The system is powered by a LiPo battery with built-in safety features. For telemetry, we use LoRa communication at 868 MHz with a range of up to 5 kilometers, enabling live transmission of mission data to the ground station. Finally, our recovery system uses sensor-based algorithms, GPS tracking, LEDs, and a buzzer to ensure quick and accurate payload recovery after landing. Thank you.
And let me walk you through the experiment behind our CubeSat mission. At its core, our mission is trying to answer a simple question: how do atmospheric inversion layers affect the way pollutants disperse in the atmosphere? Normally, pollutants disperse through vertical mixing, but during temperature inversion, a stable warm layer forms above cooler air, suppressing that mixing and potentially trapping pollutants near the surface. This can significantly impact air quality, which is why understanding the inversion layers is important. This is exactly where our experiment comes in. Investigate this. 3U CubeSat acts as descending atmospheric laboratory. After deployment, the CubeSat descends under parachute while continuously collecting temperature, humidity, pressure, particulate matter, and altitude data across different atmospheric layers. Unlike conventional ground centers, which only measure conditions at a single location, our platform captures a complete particle profile of the atmosphere. Our objective is to determine whether atmospheric inversion layers correlate with increased concentration of PM2.5 and PM210 pollutants. The collected measurements are transmitted to the ground station and stored on board for redundancy. Using this data, we reconstruct the atmospheric profile, identify inversion layers, classify atmospheric stability, and analyze how pollutant concentration vary with altitude using our ground's data processing pipeline. This allows us to investigate our key hypothesis whether inversion layers suppress vertical mixing and contribute to pollutant accumulation near the surface. To help visualize the experiment, we developed an interactive simulation platform. It allows us to see the CubeSat's descent, monitor telemetry, and better understand how atmospheric conditions and pollutant behavior change throughout the missions. Through this experiment, we hope to gain deeper insight into the relationship between the atmospheric structure and air quality. The telemetry shown in the visualization is generated using mathematically modeled atmospheric dataset designed to emulate realistic flight conditions.
Moving towards the satellite structure and materials, the dimensions of a satellite are 300 cross 100 cross 100 mm. The initial prototype was made up of 3D printed PLA-based frame, but in order to meet the weight constraints, we will create a better prototype composed of aluminum frames and rails. The remaining components to house the electronic components will be composed of 3D printed PLA-based materials. And the simulations to check the rigidity and of the structure is in progress.